Hello, this is the intro for Chapter 6, Section 1 on the normal distribution. While I do urge you to look at the textbook and read the first couple paragraphs, what we're looking at doing is understanding what a normal distribution looks like and what all the values represent. So let's go into the equation. This, if we were doing it without the calculator, if we were doing this by hand, we would have to input the mu, which is the population mean. We'd have to input the standard deviation, which is sigma. We'd have to input a couple of the values like E, which is a constant, okay, it's a never-ending non-repeating decimal, Euler's number, and we'd also have to input some pi, in this case the square root of 2 pi. But that is old school, that is the formula we used to use and still use. It's just that we now have the calculator to help us do all the heavy lifting, as it were. So what does a normal distribution look like? So if you go back to the day we did Chapter 3, and I believe that was on the top of page 142, it had this picture, and it talked about what we called the empirical rule, 68, 95, 99.7. We were talking about this data in this shape of a bell-shaped curve, also known as a Gaussian shaped curve, or a Gaussian curve. So we said that the area under the curve, all the area of the shaded region from left to right, represents 100% of all the data. So if you look at number 7, it says it represents 100%, or the decimal 1.00. This is everything for the population. Okay? We know that the mean, the median, all right in the middle of each other, in the center, I should say. Okay? Mean, median, and mode, all in the center. This is the one that occurs the most. From there, we learned that standard deviation breaks it into positions. Okay? Positions. So 1 standard deviation to the right, 2 standard deviations to the right, 3 standard deviations to the right, and likewise to the left, which would be -1 standard deviation. To the right, left 2 standard deviations is negative, and so on. We did this empirical rule, just as a reminder, that everything between 1 and -1 standard deviation represents right about 68% of the data. So if you were to pick somebody at random that took a test, they would be within 1 standard deviation above or below the average, 68% of the time. Notice the breakdown gets even deeper and further as you progress out, 34, 13, 2, 0.13%. But this empirical is the key. Okay, that's the spread. About 68% between positive and -1, 95 in between positive and -2, and 99.7 in between positive and -3. That last 0.3% is outside 3 to the left or outside 3 to the right, I should say, and. So that's the breakdown. Our goal is to realize that not everything falls directly on one of these standard deviations. So maybe we're at somewhere between 1 and 2. Maybe we're somewhere between 2 and 3, or -2 and -3 standard deviations. That value, if you recall, was once called the z-score. And we did that back in Chapter 3. We were talking about the z-score representing how far away you were from the mean. Well, we're going to do this normal distribution with all kinds of values. But the first is called the standard normal distribution. Standard normal. This is where I said you could compare things that may not even be comparable in the normal sense. No pun intended. The idea of taking a baseball player and comparing it to a chess player, or maybe someone that's the best in their field of science versus someone who's a pro bicyclist. How do we know who is the best? And the idea would be, let's compare them to all of their other folks that do those same things and see where they sit on the normal distribution. So that someone that has a 2.3 z-score in their respective sport would be better than a person that has a 1.3 z-score, okay, because they are in a higher value z-score on the standard normal. So what is the standard? The standard is when mu, the average, is 0 and the standard deviation is 1. And we will use our z-scores, this formula for z-score, to calculate exactly where that's located and then look at the area in which it encompasses. That's the idea. So we're not really using this formula up here. Okay, we're going to use the calculator, and we're going to basically use our formula that says our value minus the average divided by the standard deviation represents a z-score. That's where we're going. So let's get into the examples, and I'll show you the step-by-step on the calculator. Here we have a normal distribution, and I have already shaded everything from the left, which is like negative infinity, all the way to the left, negative infinity, up to the z-score that is 1.78. Now remember, that is a z-score. The average is 0. This represents 1.78 standard deviation to the right of the mean. Our job is to find the amount of data that that z-score encompasses on this picture. So, what we're going to ask you to do, see if I can do this on the calculator on here. We are going to talk about this as a normal distribution, okay? So it's a normal distribution, and we actually are doing a CDF. And you say, well, why is it a CDF? Why is it a combined distribution function? And that is because we are asking you to calculate the area all the way from negative infinity up to 1.78. It'd be like me calculating every single point in between until I reach 1.78, and then adding them or combining them all together. So we were talking negative infinity to 1.78, all combined together. The beauty is the calculator does it for us. If you hit the second button and go back to distributions, where we've been doing all of our geometrics and Poisson and stuff, the very first two are normal. We want the normal CDF. So you can scroll down, or you can simply hit the number 2, and it's going to ask us for some information. Now, I keep saying negative infinity. There is no button on the calculator for negative infinity. They write that as a negative 1 times 10 to the 99th power. Negative 1 times 10 to the 99th power. So the calculator puts it in that way. So I'll just write this. Remember, infinity, negative infinity, will equal negative 1 times 10 to the 99th. Positive infinity will equal positive 1 times 10 to the 99th. Those are the two values we will have to put in. So here's what we're looking at. This one starts out as normal CDF, negative infinity, we'll put negative 1 times 10 to the 99th on the calculator. And then we're going to go down to the upper, which means 1.78 is my maximum value I'm looking for, 1.78. We do not do anything with the mu, because that's 0, or the standard deviation, which is 1, and we hit paste. And that'll come up as a command line. Normal CDF, negative infinity on our paper we would write, comma, 1.78, comma, 0, comma, 1, parentheses. That is my command line. When you hit enter, you end up with your area under the curve. Now, this is going to be an area. It's not a probability, so we're going to ask you to go 4 decimal places. My final answer will be 0.9625. This represents the area under the curve. The area under the curve. And that covers you from negative infinity to the far left all the way up to the positive 1.78 z-score. And you're done. Next example. Now we're going to the right. Now we're going to go to the right. So you're going to ask yourself, what is the area under this normal distribution to the right of negative 0.76. Now that's the z-score, negative 0.76. So we're going to go from negative 0.76 as a z-score all the way to infinity. That means when I plug this in the calculator, my left value is my lower value, and infinity is my upper value. And remember, infinity we will put on the calculator as 1 times 10 to the 99th power. So our problem should be, let's find the area under the curve, which is a normal CDF. Again, it's a norm CDF combined of all the values from the lower value, negative 0.76 z-score, comma, up to infinity, comma, remember mu is the average, which is 0, and my standard deviation is 1. I know that because this is what's known as a standard normal distribution. Type that into the calculator. It's second distributions. Go to number 2, which is the normal CDF. You're going to have to clear that out because what we want to start with is negative 0.76. Enter. My upper is going to be infinity, which is 1 times 10 raised to the power of 99. Some people use that engineering, that EE button, which is up there above the comma. That's up to you. But this has to represent 1 times 10 to the 99. Don't change the U, don't change the mu, the mean, or the standard deviation. Hit paste. There's your command line, just to double check. And then when you hit enter, we find out that the area from negative 0.76 z-score all the way to the right will represent 0.7764. Done. Last but not least, one more example. It says find the area under the normal distribution between these two z-scores. They give you the z-scores of negative 125 and a positive 2. So this is still my mu. This is a z-score on the lower, and this is the z-score on the upper. like the last problem, it's going to be a norm CDF we're going from negative z-score of negative 1.25 up to a positive 2 with 0 as my average and 1 as my standard deviation. And then from there you plug it into the calculator. So yeah, you're going to hit second, and then you're going to go to your variables, your bars, your distributions. Again, number 2 is the CDF. You're just going to go ahead and type in the lower bound, which is negative 1.25. You're going to plug in your, hit enter, and go to your upper bound, which is just a z-score of 2. You're going to not touch the 0 or the 1. You're going to hit paste, and that's going to be your command line that we're going to be looking for on test day eventually. And then hit the enter button, and there you have it. 0.8716 is the area under the curve. Let me just be very clear. This means that if I gave a test and I looked at a group of people, 87% of everybody that took the exam would fall between negative 1.25 standard deviations and positive 2 standard deviations. Negative 1.25, that's 1.25 standard deviations less than the mean, and 2 standard deviations greater than the mean. 87% would fall in that range. Okay? That's where we're headed. Now, from there, we're going to ask you to go back to here. We're going to basically ask you to look at a couple problems. Oh, nope, not that one. My bad. Let's go back to here. I had those examples in a couple places. These were different examples that we were playing with, but anyway, still could do them. We're going to ask you to do these exercises. I'll help you out. Number 6, what are 2 other names for a normal distribution? I said them at the beginning of this lesson. One is called a Gaussian, G-A-U-S-S-I-A-N, Gaussian curve. I hope that's all spelled correctly. And the other is the other possible name is a bell curve. Okay? We're going to ask you to do 7 through 13 right here. Notice between 0 and 0.98, between 0 and 177, to the right of. Let's just be clear. If it says to the right of, here's 0, here's 0.29, to the right of would be all this. So this is my lower. Infinity is my upper. I'm not going to ask you to draw all the pictures, but it's important you understand how and where these come from, because we're going to kick it up a notch in a couple of days, in a day or two. So those are the examples. That's the homework, 7 through 13. Should not take you super long. Have a great night. We'll see you tomorrow.